everybody's okay now that everybody had lunch, so let's resume our activities with the next lecture by Jaroslav.
Okay,
Thanks.
thank you very much. So we ended this introductory discussion with introducing Spinor-helicity variables. We said that we can write for massless particles on shell, okay, on shell, p square is equal to 0. We write the form momentum in a factorized form using two spinors, lambda and lambda tilde. And a little group transformation which leaves the momentum invariant. In terms of the Spinor-helicity variables, is just rescaling lambda to t lambda and lambda tilde to 1 over t lambda tilde, where t is complex, which leaves obviously the momentum invariant. Now, here we said that the momentum now we will consider in general complex. Despite, for the real scattering, or for the real particles in the real world, P should be real, and that then relates lambda and lambda tilde together. If it is complex, then they are independent. Yeah, the thing is that even when P mu is real, sorry to talk more about this real complex, but if P mu is real, then lambda and lambda tilde are related by complex conjugation, but the lambda and lambda tilde themselves are still complex. Yeah, so, but they are related by conjugation. In case P mu is complex, then they are independent. Okay, so now let's calculate some momentum invariants, how they look like, or well, scalar, for two different momenta. So let's consider P1. So we write it as lambda 1 alpha, lambda 1 lambda tilde, and then also P2. So for two different momenta. Yeah, at some point I will start dropping this sigma, which is always there. Okay, so we just wrote this change of variables for two momenta. And now let's calculate S12, which is P1 plus P2 square. And because we are on shell, P1 square and P2 square are 0. We can rewrite it. P1 dot P2 plus P2 square. This is 0. This is 0. And we get 2 times P1 dot P2. Okay? And now we use these formulas and rewrite it in terms of lambda lambda tilde. And that would be the first surprising thing, which is specific for 4 dimension, that this expression now factorizes into 2. Yeah, here it's just one expression, but now if we plug for P1 and P2 here, we get 2 times sigma mu alpha alpha dot, and then sigma, now I put mu and as a lower index, let's say beta beta dot, and then we get lambda 1 alpha, lambda 1 tilde alpha dot, lambda 2 beta, lambda 2 beta dot tilde. Okay, Now, there is some summation rule. For that, this is now contracting over mu, summing mu from 0 to 3. And what this turns out to be is epsilon alpha beta, epsilon alpha dot beta dot. Okay? So then we rewrite S12 as epsilon alpha beta, lambda 1 alpha, lambda 2 beta. I just divided. This means nothing. Yeah, it's just a product of two things. But just to emphasize that this is now factorized into 2. And we just use some notation. So this is a usual way how we denote it. So this is a contraction of these two indices. They are contracted by the epsilon tensor. This is just a 2 by 2 antisymmetric matrix. This is the same thing. And we just use notation for that so-called angle bracket 1, 2. And this is a square bracket 1, 2. Okay, so in the end, S12 factorizes as a product of angle bracket 1, 2 and square bracket 1, 2. Again, it's just a change of variables. This would only work, but this factorization into two pieces would only work in 4 dimensions. Yeah, so in 4 dimensions, something special happens. And we will see the physical significance of that later. Any questions about this? So we can take any dot products of momenta and turn it into these two types of brackets, angle bracket, square bracket, when the entries are just the lambdas, and this means contraction. You can also think about it, this is contraction using epsilon tensor. This is just a 2 by 2 determinant. Yeah, when we put lambda 1 kind of comma 1, lambda 1 comma 2, lambda 2 comma 1, lambda 2 comma 2, where this thing after comma is just the components. Yeah, 2 by 2 determinants are these things. Does it make sense? Yeah. Yes. What did I swap? Oh. Yeah.
When we got to this line from the previous line, we swapped the lambda 2 beta and the lambda 2 1 alpha dot.
So the ordering, so this thing is antisymmetric, right? But the ordering here was this first, this second, and that was contracted with that.
Yes, so come to this line from the previous one.
Okay.
This one, so here is lambda 2 1 alpha, and then lambda 2 beta, and then start with those numbers.
Sorry, did I denote something? Well, I don't see the minus sign, but it's possible that I overlooked some minus sign. But we have these two expressions. We have these epsilons. We contract these two. This is, the epsilon is alpha beta, so alpha goes first, beta goes second. This is 1, 2. Here, alpha dot goes first, beta dot goes second, so this is 1, 2 as well. Yeah. Now, there are different kind of convention when there is a minus sign. You are right. Yeah.
I think we have a question from Zoom as well.
Yes. Variables for more particles. Yes. Yeah, it's possible, and we will do it. So this is just the Mandelstam for P1 and P2, but you can do it for any pair. Yeah. So just a simple generalization, well, which is kind of trivial. We just relabel things. So Sij, which is Pi plus Pj square, is equal to Ij, where now these labels are particle labels. Yeah, so we use the Spinor-helicity variables for particle I and j, and then doing this again for this Sij things factorize. Now, as I mentioned here, so maybe, yeah, in some, definitely in some conventions there is a minus sign. Here I try to use the convention only with plus sign. But these brackets are antisymmetric, because these are just 2x2 determinants, so they are antisymmetric. So flipping the labels gives a minus sign. And we can also here calculate multi-particle invariants. So for example, some standard notation, we can calculate S123, which just means P1 plus P2 plus P3 square. Okay, so this is, I leave as an exercise that if you use repeatedly this transformation that we did here, you should get 1, 2, 1, 2, 1, 3, 1, 3, plus 2, 3, 2, 3. So here we see that for these multi-particle invariants, the things don't factorize. You can write them using these Spinor-helicity variables, but only for the two-particle Mandel-Stamps, the things factorize directly into 2. Yeah? And then, for example, why I emphasize so much that it factorizes, because saying that S12 is 0, you have to choose which one do you want to send to 0, this one or this one. And they will be physically different. Yeah, there will be a big difference between sending this to 0 and this to 0. And this is only especially in 4 dimensions. If we are in 5 dimension, S12 is 0, there is just single option. You just send S12 to 0, yeah, P1 plus P2 square. But in 4 dimensions, there are 2 options how to make it 0, which is not visible if you write it using momenta, despite even in momenta there are somehow 2 options. But in terms of the Spinor-helicity variables, you directly see it as 2 different options. Any questions here before we move forward? Up. So let's discuss few more properties of these Spinor-helicity variables and the kinematical invariants. So one property is so-called Schouten identity. Mathematically, it's just a trivial statement about these epsilon tensors. So if we have bracket 1, 3, and 2, 4, let's say this angle bracket, and we take a product of these two, we can rewrite it as a sum of 2 things with reshuffled labels. 1, 2, 3, 4 plus 1, 4, 2, 3. And you can easily prove it because as we know this, we can write as epsilon, let's say AB, lambda 1A, lambda 3B. This is equal to epsilon CD, lambda 2, C, lambda 4D. And this statement is nothing else than the statement about the products of epsilon, reshuffling labels there. Yeah, there's different names in mathematics. So you do the same thing for here, and then it's just a three-term identity for these epsilons. Okay, so this is one identity which is very useful. The other thing which is often defined is so-called, or it's a mixed bracket, which is both the angle and square brackets. Already the multi-particle kinematical invariant had also this combination, but whenever you see bracket which looks like this, which we will then have in the recursion relations when you have kind of angle here and square here, this I just even defined as a chain this 2 plus 3 is really P2 plus P3 in this matrix form, AB, so, or AB dot. So you dot the A index with lambda 1 and the B dot index with lambda 4 tilde, and you get this. Yeah. So I will also kind of leave it as an exercise to show this. But it's really just the way how to you have to just rewrite this. The P2 plus P3 means P2 plus P3 momenta in this matrix form. Okay. Any questions?
So why is different in 5 dimensions?
So in 5 dimensions, we cannot use these Spinor-helicity variables.
No, but you say that this equation has 2 solutions in 4, but
in 4.
only 1 in 5.
In d dimensions, there's only 1 solution. So if you send S12 to 0, and you ask on where you move in the kinematical space, you make the momenta special. There is only 1 solution. But in 4 dimension, it factorizes into 2. So you have 2 options how to send it to 0. You either make this bracket 0 or this bracket 0, and they are different solutions. Yeah. So it's only in 4 when this special thing happens. And we will see it as something to do with special kinematics in 4 dimensions. Anyway, yeah. Yes. Yes. Yeah, then you can do that. Yeah. Well, okay, in 5 dimension, in a sense that they must span the whole 5-dimensional the full 5-dimensional space. Yeah, let's say, okay, there are always special things if the number of momenta is smaller than the number of dimensions. But let's say that we saturate it. Yeah. Then this special thing happens here. Okay, good. So now there is one important constraint on this lambda lambda tilde, which just comes from the momentum conservation. So the momentum and energy are conserved during the scattering process. So if we have a scattering amplitude, I said that we can always consider all momenta incoming or outgoing. Yeah, that's the standard. Then in the end, if we want a particular process, we have to flip some directions to say this is incoming, this is outgoing, but we can consider the amplitude is the same. So we can consider all of them incoming, let's say. Then the form momentum is conserved. So sum of the pi from 1 to n for the n particle process is 0. Now, in terms of the Spinor-helicity variables, this becomes a more complicated condition because it's quadratic. Yeah, we can kind of factor out, this sigma matrices, which change the mu to AA dot. But then we have this condition. And we are summing over I from 1 to n, but this is a quadratic condition. Yeah, it's a product or bilinear in the lambda and lambda tilde. Yeah, it's a condition on this product that must be 0. Yeah, so it's a non-trivial relation. In original momenta, this relation was easy because we can just express Pn in terms of P1 up to Pn minus 1. But here the condition is just more complicated, yeah, because it relates lambda and lambda tilde for different indices. Yeah, you can also, these are 4 conditions, as this is 4 conditions. You can kind of choose some 4 independent conditions and let's say remove some of the lambda, lambda tilde, express them in terms of the others, but it's a more complicated condition. It's quadratic in the parameters. Yeah, we parameterize lambda and lambda tilde by some, let's say, some entries AI, BI, CI, DI. It's quadratic, or not quadratic in each. It's bilinear in each, but it's quadratic in total. Okay, so I will just wanted to stress this is a non-trivial condition here. Okay. So now let's go farther. So we have these Spinor-helicity variables. We know how to express momenta. But if we calculate amplitudes, they don't depend just on momenta, but also at some spin structure. Now, for scalar amplitudes of scalars, there will be kind of nothing new because the scalar amplitudes only depend on momenta, indeed, because there is no spin. Everything will be written in terms of Sij, so we can just express it using these variables if we want. But we don't get so much mileage, yeah, because we just express Sij as this product, and that's it. However, in theories with spin, the Spinor-helicity variables will be very useful in writing down the amplitudes. So let's now look at spin 1 particles. And the spin structure in quantum field theory is expressed or is captured by the polarization vectors. So the polarization vector epsilon mu, it's a 4-component vector. We have to impose conditions on this epsilon mu because for massless particles we have only 2 polarizations, yeah? Epsilon plus and epsilon minus, which are typically chosen as the components of that 0, 1, plus minus I, and 0. But if we write expressions in terms of epsilons, the amplitudes depend on epsilon.p and epsilon.epsilon. We have a problem, and that's actually the core of the problem why when I, in the beginning, show this Park-Taylor formula, why it's so simple, while if, in contrast, when you write it in terms of Feynman diagrams, it will get incredibly complicated. And that's exactly this thing, that the epsilon has 4 components, but it should really capture 2 degrees of freedom for positive and negative helicity. Yeah? Because for massless particles, we have only 2 helicities, plus and minus. Now, for the amplitude, for spin 1, massless spin 1 particles, like gluons or photons, the amplitude will depend on these epsilons and also momenta. And must be invariant under the gauge transformation when we take the epsilon and shift it epsilon plus, this is some epsilon I for particle I, plus alpha times pi. Okay, right here. Okay, and the amplitude must be invariant under it. Yeah, this is the condition that we impose in order to remove the unphysical degrees of freedom from here. Now, the individual Feynman diagrams are not invariant under that. They will depend on alpha, but the amplitude will be independent on alpha. Yeah? And yeah, as I said, that's one of the source of the problems why the complexity grows for Feynman diagrams. Now, in terms of these Spinor-helicity variables, we can also rewrite the polarization vectors in terms of them. So for the plus helicity, the polarization vector, again, has this sigma matrix, which just turns these labels into these spinor labels. And let me just write it, and then I will explain what it means. Okay. Okay. So this is a vector, has a space-time index mu. We turn it into two indices, A and A dot, as we did with the momentum itself. Now, this is a product of two spinors, one with A index, the other one the A dot index. For the plus helicity, the A dot index is carried by lambda tilde for that particle, for which we write the polarization vector. And the A index is carried by some auxiliary field, auxiliary spinor. Okay. And then we divide it by the angle bracket, which is a contraction of the spinors with this A index of this spinor and the lambda of that particle. And similarly for the negative helicity, spin 1 particle, the A index is carried by lambda, the A dot index by some auxiliary spinor eta tilde, and it's divided by a bracket which contracts the lambda tilde of that particle and the eta tilde spinor. Now, this depends on some auxiliary spinors, this eta tilde, but the amplitude will not depend on it. Yes? So the epsilon mu has 4 components, yeah, and we have only 2 polarizations, yeah. So the epsilon should have only 2 degrees of freedom. That's kind of the problem when we use the Lorentz invariants, because they have space-time index, which has 4 components, but our physical object has fewer degrees of freedom. Yeah, so this has only 2 degrees of freedom. So we have to impose constraints on this in order to move from 4 to 2. Yeah, and yeah, one of the constraints is the constraints on so this is the constraint, which basically, if you want, it comes from saying that it removes the component of epsilon, which is proportional to p. Yeah, so tells us that if we do this change, then the amplitude, if we do this transformation, the amplitude shouldn't change. Yeah, shouldn't change when you move epsilon in the direction of p. Yeah, or in a, yeah. And this transformation, this gauge invariant transformation here, it comes also, it's actually, the equivalence of that is at the level of Lagrangian. Yeah, when you take a mu and shift a mu plus d mu phi. Yeah, so this is the momentum space version for that for epsilons. Now, this gauge transformation here, the fact that the amplitude does not depend on alpha, is a statement here at this level that the amplitude does not depend on this epsilon, these two auxiliary spinors. Yeah, so so the amplitude doesn't depend on them. So we can make any choice we want, but the amplitude doesn't depend on this eta and eta tilde. Despite these epsilons do depend on them, but once you plug them in the amplitude, once you calculate the amplitude, they will drop. And this is the analogous statement, is that when you do this transformation, this shift, then the amplitude also doesn't depend on this parameter. Yeah? Yeah, but they kind of appear in particular combination. Yeah. Yeah. So yeah. It is a different representation. It's not completely obvious, but it here shows up as eta over eta, so you can also rescale it. Yeah. So the kind of number of non-trivial conditions is here is the same as here.
Can you repeat that for the
yeah. Is there any physical interpretation? You mean of these etas or of these epsilon plus? Of the epsilons. Well, right, yeah, so no, this is kind of a covariant way how to write this, modulo these transformations. Right. Right, but you note that here the x, y, z, t are kind of reshuffled in these spinor variables. Yeah, because they are changed by this matrix sigma mu. So so we cannot like here easily see in which direction it points in the original space-time. Yeah, so here we see where it points in this A dot space. Yeah, it points in the lambda tilde direction, and it points into this auxiliary direction. Yeah, which we can choose randomly. So this obviously is not physical. Here the same thing, but it's just reversed. Yeah, so you can think about it that for the plus helicity, the A dot, yeah, in the A dot direction it points in the direction of lambda tilde of the particle, for which this is the polarization vector, and the same thing for the minus, just in the direction of this lambda. Yeah, it's the way how to get these expressions is that you show they satisfy the same properties of these epsilons here. Yeah, so it's not that trivial to see that it should look like that, but you impose the same conditions that are imposed on epsilons that they should satisfy are satisfied by these representations. Yeah. So, but I don't have here any kind of a priori intuition how it's related to pointing in these directions. Yeah, at least not me. But one thing which is important to note here is that are these little group transformations. So we said that this lambda lambda tilde, they had 4 degrees of freedom. Well, for complex momenta, they were complex. But we had to remove one of them because we only wanted to describe 3 degrees of freedom because the massless momentum has only 3 degrees of freedom. So so just the recap that for lambda going to t lambda and lambda tilde going to 1 over t lambda tilde, the momentum stayed invariant because the product of lambda lambda tilde was invariant. However, the polarization vectors are not invariant. Yeah? If we scale for particle I, if we scale lambda like that and lambda tilde like that, it will change. Yeah. So epsilon plus, we see that it's lambda tilde in the numerator, so it will be 1 over t, and lambda in the denominator, so again 1 over t. So under this transformation, it will scale like 1 over t square. And epsilon minus has lambda in the numerator and lambda tilde in the denominator, so it will scale like t square epsilon minus. Okay? So that makes sense because also the amplitudes are not invariant. Yeah? The polarization vectors in the original representations are not invariant under the little group transformations. Yeah? And also in the Spinor-helicity variables are not invariant. However, it tells us something important. So it tells us directly how the amplitude should behave if we do this little group transformation. Because the amplitude as a function is linear in polarization vectors for each particle. Yeah? If you just imagine the Feynman diagrams, on the kind of outside of Feynman diagrams, for each leg, we have one polarization vector. Yeah? So you can think about it, the amplitude, as a big product of polarization vector 1, okay, with some labels, mu1, polarization vector 2, polarization vector 3, up to polarization vector n, mu n, multiplied by some function, I may also call it a, which has all these labels, mu1, mu2, up to mu n. However, this function is written only in terms of momenta. Yeah, this is written only in terms of momenta. The dot products of momenta or the momenta themselves with the indices, but this function a is invariant under the little group. So all the transformations of the little group of the amplitude comes from the transformations of the polarization vectors. Okay? Yeah, this is the amplitude. Which means that the amplitude also transforms like this under the little group transformation. Yeah, sorry, this argument is very fast. It uses the Feynman diagram notion that everything is linear in polarization vectors, but I still like it. Yeah. So the amplitude for spin 1 particles transforms like this. So suppose that we have particle 1, which has plus helicity and some other particles. So if we do the little group transformation, lambda 1 going to t lambda 1, lambda 1 tilde going to 1 over t lambda 1 tilde, it transforms like 1 over t square, this amplitude. And if we do it with for particle which had negative helicity, it transforms like t square. And we can do it for all particles. Yeah, transformation. Does that make sense? Any questions about this? So here we a priori already know how the amplitude, which is function that we don't know, how it transforms if we do these rescalings. Yeah, with no extra knowledge. We don't need to know what is the theory, anything. Yeah, just from the helicities, we know that the helicity is positive or negative, and there is a spin 1. Then we already know how it transforms. Okay? Okay. Yeah. Yes. Yeah, yeah. Yeah, for every positive, you pick your particle. If it is positive, you do this rescaling, you get 1 over t square. If it is negative helicity, you get t square. Yeah, yeah. Yeah, but you have to pick the helicities. Yeah, so this also brings us, we see that this is such a kind of interesting condition that it leads us to conclusion that we should consider helicity amplitudes. So we should fix helicities of external states. And because we are massless, they are only plus or minus. Yeah, they can have different spins. Yeah, it can be spin 1, spin 2, 1/2, 3/2. Yeah, anything. Yeah, only the spin 0 has. It doesn't have any helicity. But so we pick the external states. What are the helicities? We know how they transform under these little group weights. So from that, we can already do some checks. So this is not a derivation of the formula. But this Park-Taylor formula I wrote before was a 3-level amplitude for the following helicities. Yeah, 1 minus, 2 minus, 3 plus, 4 plus, 5 plus, 6 plus. And I write the formula again, and we can just check that it transforms properly. There is something very special here because it only depends on these lambdas, not lambda tildes, only on these angle brackets, not square brackets. So we can now check these properties. So particle 1 has a helicity minus. So we now rescale all lambda and lambda tilde. Well, the lambda tilde doesn't show up in the formula, so we only rescale lambda. So there are 3 ones in the numerator, and there is 1 in the denominator. So indeed, it gives you t square. The same thing for 2, and now for 3, we have only 2 3s in the denominator, so it will scale like 1 over t square. Okay, so this formula passes that check. Yeah, doesn't mean it's not a proof that it's an amplitude for this amplitude, but yeah, it passes the consistency check. Yeah, you will derive it later. Any questions here? Yeah. Yes, question. Yeah.
Sorry, the a mu over there, like, does it depend on the momenta as well, or like?
Yeah, it depends on momenta, only momenta.
Only momenta, okay.
Only momenta.
Okay,
yeah, because the helicity function for each particle, you get a helicity function. Yeah, for scalars you get nothing, you get just 1. Yeah, for then you have the fermionic functions or the polarization vectors, polarization tensors, and so on. But for each external state, you get 1, and then it's contracted to something here. Yeah. But the point was that this object was built only from momenta, nothing else. We have momenta and polarization vectors. Polarization vectors we factored out. We have only momenta. Okay. So this thing is invariant under this transformation. While this is not invariant, but it's not invariant in a very localized matter. It's non-invariant only through these epsilons. And for each particle, only 1 epsilon. So knowing how the epsilons transform, we already learn how the amplitudes transform. Yeah. So from that, I gave you this formula, and I said it's a 6-point amplitude for gluons, which are spin 1 massless particles, of these helicities. So I didn't prove that this was the right formula, but there was a consistency check on this, which was that it had to satisfy these conditions, and it did satisfy it. Yeah. We will later prove it that it's indeed the correct formula. But if it didn't satisfy it, it was definitely wrong. Yeah.
I was just going to ask, like, later on, we're going to give an explicit formula for the a mu, or it doesn't really have?
Like, that depends on the amplitude. Yeah, it's depends like which amplitude for which helicity. Okay. Well, here it's not, helicities were not chosen. How many points? Yeah. No, I was just saying that in the amplitude you can factor out part which depends only on momenta, and which depends on polarization vectors, because the polarization vectors were not invariant under these little groups. And then from that we derive how the amplitude.
All right, thanks.
Okay, good question. Yeah, one more question. Yeah, so this formula was only for...
Sorry, could you repeat the question?
So here I just chose some helicities. Could I choose it differently? Was there any condition? Yeah, that's a very good question. So this amplitude was for this helicity. If I relabeled 3 from plus to minus, you will get slightly more complicated amplitude. It had to satisfy the same condition as here stated. If you flip this minus to plus, you will find, using some arguments, there is no such an amplitude. And the amplitude is indeed 0, because 0 is the only thing which is invariant. Also, if you flip both of them to only pluses, it's also 0. Yeah. Well, there is an amplitude, but it has kind of higher power counting. Yeah. The amplitude with only Young-Mills power counting, this is in Young-Mills theory, will not exist. Yeah. Which is something you can... I don't know, maybe there is some argument, but if you calculated the amplitude using epsilons and p's, polarization vectors and momenta, the amplitude will be the same for any choice of helicities, because you haven't chosen the helicity yet. It will be some gigantic formula, and will be basically these 220 Feynman diagrams. There is no simplification of that. Now, you would pick the helicities, and you will see how things kind of magically shrink either into 0, or into this formula, or into slightly more complicated formula. Yeah, but it's kind of the difference. Yeah, so here the helicity amplitudes written in terms of lambda, lambda tilde are very simple, but you have to choose the helicities. So if you choose another helicity, you have to calculate it again. The one using polarization vectors and momenta works for any helicities. You haven't chosen it yet, but then the complexity grows massively. So so anything which has 2 minuses and the rest pluses looks like this. And the one which has 3 minuses and 3 pluses, slightly more complicated. It's basically a sum of 3 terms. Yeah. Each term kind of transforms correctly under these little groups, but it has some other deficiency, which we will see. It will have some spurious poles that must cancel. Okay, very good. So this was for spin 1. I just randomly chose spin 1. So sorry. So this was spin 1 that we did here. No, it's not. Yeah, it's not conserved. Yeah. You can have, okay, not generally. There are special cases when it's conserved. For example, in the Born-Infeld action, it is conserved, but it's typically a consequence of some symmetry or some duality. Yeah, but here it's in Young-Mills it's not conserved. Yeah, there is still some restriction. As I said, you cannot have, for example, all pluses. Yeah, but in general, as you can see here, it's not conserved. Even the fact that it's not conserved is also in the name of that amplitude. We will do it later, but this is called Park-Taylor from the names that discovered it. But it's also the amplitude which maximally violates the helicity. Yeah, the conserved one would be this one, but now we violate, and unfortunately in this case the maximal violation is to flip only 1. So this is maximally helicity violating amplitude. Yeah. Yes. Question.
So how would a complete proof of that proposition look like, and without computing Feynman diagrams?
We will do it using recursion relations.
Okay.
Yeah, once we introduce them, it would be basically a one-line argument then. Yeah, actually there is a slightly more sophisticated proof using symmetry, but this is doing really like detour, yeah, because, okay, well, let me say, the amplitudes of gluons at 3 level, you can add any amount of supersymmetry you want, and you get the same amplitudes. Yeah, so this is non-supersymmetric, but we can supersymmetrize it and add maximum number of supersymmetry, which is n equals 4 supersymmetry. And the amplitudes of these gluons will be the same in supersymmetric and non-supersymmetric theory. But the supersymmetric theory has his invariant, this n equals 4 super Young-Mills under conformal symmetry and extra hidden dual conformal symmetry. So the 3-level amplitudes have also this symmetry. But it's only true for 3-level, because once you go to loops, everything is different. The supersymmetry matters. So there is a symmetry argument for that, but let's say that This is only something which people could do in last 10 years, yeah, make this argument. While the argument based on this, the helicity could be done much earlier and was done probably. Okay, let me now move from spin 1 just to general spin. Because I just said how the transformation works for spin 1 particles. But there is a generalization for any spin. So let's say I have amplitude and I have particle I, which has negative helicity for spin S. Then the little group transformation that we did there works in a similar way, but just instead of t squared, we get t to the 2s times the amplitude. What did I write here? And for the plus helicity, it's 1 over t to the 2s. Yeah, so we can do it, let's say, for gravitons. We will actually then do it later. We will do some nice exercise. Yeah, for any spin. For spin 0, obviously, this thing is completely invariant because there are no spin functions. Everything depends just on momentum. Yeah, note again, this is just a trivial reminder. If we have massless spin S particle, it has still only 2 helicities, plus or minus. So, okay, good. So let's do, okay, I have one example here. Yeah.
I'm a bit confused, but like, if helicity is like a spin, right?
Yeah.
And if helicity is like a spin, why is it not conserved?
Why it should be conserved?
Because angular momentum is conserved.
Well, this is an internal spin. That's not conserved in particle, yeah, in the interaction. Let's just consider gluons. Yeah, you have free gluon interaction, and obviously for free particles, it cannot be conserved. Yeah, no, it's just not conserved, yeah, the helicity, the internal helicity. Yeah. It's a good question.
Can you repeat the question?
Yeah, is there a
Yes.
compact formula for spin S? Well, that will be kind of one of the very nice results of working with these Spinor-helicity variables. We will be able to quickly prove, without any extra assumption about quantum field theory and so on, that there are no interacting quantum field theories beyond spin 2. So we will be able to write amplitudes for 3-point for any spin. That will work. But once you start to write the 4-point amplitudes, you will be restricted to very small menu of spins, yeah, where spin 2 is the largest one, and yeah, which is the graviton. You are even pushed to have general relativity there without any extra assumption. And spin 3½ must be the gravitino. There is no other option. And then we will have spin 1, 1½ and 0. But from some simple assumptions that we will have about factorizations, we will be able to prove that there are no, let's say, quantum field theory on spin 3. Yeah, which of course is known, but yeah, the amplitudes argument for that is pretty cute. Okay, let me here. So this will I leave as an exercise. I can give you an amplitude. So let me give you a 4-point amplitude, written using these Spinor-helicity variables. And just for these transformation rules that under the little groups, you can directly tell, you cannot prove that it's a correct amplitude, but you can directly tell what are the helicities of the individual states 1, 2, 3, 4. Yeah, so what are the spins or helicities, yeah, for particles 1, 2, 3, 4? Yeah, you just look at how the amplitude must transform, how it transforms, and from that you can quickly learn it. Okay, any questions here? Yes.
So you mentioned that this also is to some extent applicable to the d = 3, right? So that would be like.
Yeah, in a very yeah. Anyway, I don't want to talk about it.
I was just curious because that would be like scattering in the plane, and I remember there are anyons there, like fractional spins.
No, well. Yeah, there is even some theory about continuous spin here that you can do. Yeah, these amplitudes don't satisfy the same properties we are used to, but there is still discussion if the amplitudes for fractional or even continuous spin make sense, yeah, and how they should look like. Yeah, yeah. Well, I don't know about it much, but that's definitely kind of an open debate. Yeah, they will not satisfy some of the conditions that we have here, but the question is how can we relax some of them? Yeah. Just going to 3 dimensions and the Spinor-helicity variables. Yeah, you can use the Spinor-helicity variables in 3 dimensions, but you have to impose extra constraint to restrict your kinematics to 3 dimensions, which makes it ugly. Yeah, and the question is if it is then if it makes sense to use it or not. But yeah, it's possible. It's possible to do it. Yeah. Okay, so so if there are no questions here, we move further. There I am. Okay, so we start with the discussion of 3-point amplitudes. So let's finally construct some amplitudes. And we start with 3-point. They are very special, you will see. They are the most beautiful amplitudes. Now, it's very important that the momenta that we consider here are complex. Because if you restrict yourself to real momenta, it has no solutions for only 3 points, and there are no 3-point amplitudes, which makes sense. We don't see in the real world any 3-point scattering. It comes from constraints, yeah, because for 3-point we have momentum P1, P2, and P3. These momenta are on shell. So P1 square, P2 square, and P3 square are 0. And at the same time, they satisfy momentum conservation. P1 plus P2 plus P3 is 0. Yeah, if we consider the 3-point scattering. Okay, yeah, I kind of drop here the mu in, yeah, the space-time index. And this is a lot of constraints. It almost cannot be solved. Yeah, it almost forces you to have all the p's being 0. If you demand that they are real, indeed the only solution is that all the p's are 0. There's just no solution. But if you allow complex, then you can solve it. So it has solution for complex momenta, not for real momenta. And we will see what these solutions are, and they can be nicely expressed using these Spinor-helicity variables. So let's just do it. So we said that P1 square is 0, but P1 square is also P2 plus P3 square from momentum conservation, because we can express P1 as minus P2 minus P3. And this we already know that it's angle bracket 2, 3 times square bracket 2, 3. And that is 0. Then we do the same thing for P2 square. This is P1 plus P3. This is 1, 3 times 1, 3. And this is 0. And the same thing for last one. This is P1 plus P2 square, which is 1, 2. So a lot of things are 0. Now, because as I emphasized before, this condition factorizes into 2. So you can basically pick which one do you want to send to 0, this one or this one. And here also, this one or this one, this one or this one. As it turns out, there are only two choices that you can make, which don't make everything 0. Yeah, there is always choice when all the lambdas are 0, all the lambda tildes are 0. That's not the choice we want to make. Yeah, it makes us no scattering. So in order to satisfy these three conditions, we either send all the angle brackets to 0, all the square brackets to 0. Yeah, any other choices basically gives us only trivial kinematics. So there are two solutions. So the first solution is that 1, 2, 1, 3, angle brackets, and 2, 3 are 0. What does it mean? We said that this is just 2 by 2 determinants of lambda 1 and lambda 2, lambda 1, lambda 3, lambda 2, lambda 3. So saying that this bracket is 0 means that the lambda 1 is proportional to lambda 2. Yeah, they are proportional. And these guys are proportional, and these guys are proportional. So this means that the lambda 1 and lambda 2 and lambda 3 are all proportional. Yeah, does it make sense? You can think about it as 2 component vectors for this purpose. Yeah, and the second solution is that the other type of brackets are 0. So these lambda tildes are all proportional. Okay, does it make sense? If we demanded that the momentum is real, then lambda tilde would be a complex conjugate of lambda, which means that if lambdas are proportional, also lambda tildes are proportional at the same time, which means that all momenta point in the same direction. Yeah, and so there is no scattering. Yeah, here. Yeah, but if we keep them distinct, in the first solution, these guys are proportional, but not the lambda tildes, and here the other way around. Okay, good. But this now allows us to write the 3-point amplitudes. So now let's consider arbitrary 3-point amplitude. For any spins, for any helicities, it can take only 2 possible forms. Either it's built only for the angle brackets. This is this solution because the square brackets are 0. Or it's built only from square brackets. Yeah? So it either has this form, or it has this form. We haven't assumed anything yet. Yeah, we just solving 3-point kinematics, nothing else. Okay. Well, why? Because the other set of brackets are 0. Yeah, here all the lambda tildes are proportional, and all the brackets are 0, or all the lambdas are proportional, the brackets are 0. So we can either express it like that or that, depending which solution we pick. Okay? Any questions here? Does it make sense? Yeah. Yeah, for massless particles. No scattering. For massless particles, no. Yeah, so here it's complex. This is not about real scattering on any colliders. Yeah, here everything is complex. Yeah. So sorry. Right. Complex. Okay. So let's now calculate some amplitude. So we already know the rule about the little groups, little group transformation. So we can just assume that the amplitude has either the first form or the second form. And now knowing the helicities, we can just fix these coefficients A1, A2, and A3. OK? So let's take following amplitude. So I do it for just spin 1. Yeah. So 3-point amplitude, which has 1 minus, 2 minus, 3 plus. And this is for spin 1. Yeah, we will later do different spins. Well, let's just do spin 1 for here. So the amplitude either takes the first form or the second form. So we know that for the negative spin 1, if we do this little group transformation, it transforms as t squared times a. And for plus, it transforms as 1 over t squared times a. So we do the first case, and we write 3 equations for 3 unknowns, a1, a2, and a3. Yeah? For each particle, we get 1 equation, and we solve for a1, a2, and a3. So this is an exercise. I will just write the result. So solve for a1, a2, and a3. And the solution looks like this. 1, 2 cube over 2, 3, 1, 3. That's if the first case was true, so all the lambda tildes were proportional. So this is kind of 1. Then we can consider the second one, where all the lambdas are proportional, and solve for B1, B2, and B3. So A3, in that case, is 1, 3, 2, 3 over 1, 2 cube. You will find this solution. Now, only one of these amplitudes is correct. The other one is wrong. Yeah. Both of them pass the check on the little groups. So they are both candidates for the right amplitude. Yeah. We nail it down to 2 options. But only one of them is correct. The other one is wrong. In other words, for this amplitude, you don't have a choice to pick this solution or this solution. The solution is given to you. Now, it's a slightly subtle argument. Can anybody tell me which one is the correct one? It's not related to anything what I said so far. The best way how to see it is actually from the Lagrangian. OK, anyway, from the Lagrangian, it's easy to see it. Which one can be the correct one? Well, which one is the correct one? You have to tell me also the argument, because people who know how the MHV amplitude looks like can immediately see what it is. But any ideas? The first one is correct. The reason for that is that if you, yeah? Okay, it looks like the one I wrote before. OK, it's a good argument. Now, the reason for that is that if you actually count the number of derivatives. Yeah. So if you think about where it comes from the Lagrangian. So the Lagrangian term it comes from is something like a squared dA. We don't need to assume it. Yeah, it's something, these amplitudes are given to you independent where it comes from. But here, you know that the 3-point amplitude has a derivative here. The polarization vectors don't carry any derivatives, right? And the bracket scales like a derivative. So here there are 3, and there are 2 here. So this scales as m when, like, kind of the derivative or the momentum has the same dimension as mass. This one scales like 1 over m. So it would have to come from the term which is not local. Yeah, it would be like 1 over derivative. Yeah. Yeah, if you are happy with non-local QFTs, yeah, you might consider it. Yeah, but in the local QFTs, this is the right and this is not the correct one. Yeah. In the end, you can just formulate the overall condition that the mass dimension of 3-point amplitude must be positive, yeah, or at least 0. It cannot be negative. And this one has a negative mass dimension, while this is a positive. Yeah. So this is the right solution. But you can see here that just in general, for any spin, this was for spin 1, but for any spin, there are only 2 options for the amplitude you can get. From these 2 solutions, you solve for the little groups here. You solve from the little groups for the coefficients here. You solve it for here, and then you pick the amplitude which has a positive mass dimension. And then for any choice of spins, you get a 3-point amplitude. Okay, so let me just formulate that, and then we end this session discussing the 3-point amplitudes. So arbitrary three-point amplitude which has helicity H1, helicity H2, and helicity H3. You make an ansatz, the same as we did here. You solve for A1, A2, A3, and B1, B2, B3. And you pick solution with positive mass dimension. Yeah. Okay. Anyway, this is kind of mass dimension of that is positive, or actually, sorry, at least not negative. Yeah. Okay. Now here we haven't assumed anything about trees or loops or anything. Yeah, there was nothing which went into it. We didn't have even any Lagrangian. The only thing that I kind of cheated was like picking which one is the right one. So this is an all-loop argument in the following sense. Yeah, so for the 3-point amplitude, the kinematic part of the amplitude always look like this. Yeah. Now it can be multiplied by some numbers, like by a coupling constant, running coupling constant, or something, some divergent thing or something. But the kinematic part must be this. Yeah, the rest in the 3-point amplitudes, if it is at loops or anything, must be something which doesn't have any kinematical dependence. There is kind of the moral why at 3-point, the little group was so strong that basically it fixed the amplitude completely, is that from these 3 momenta, P1, P2, and P3, you cannot cook up any kinematic invariant. All of them are 0. Yeah? So you cannot cook up any cross ratio, nothing that you can do from that. Yeah? So everything is carried by just this factor. It's not true at 4-point. At 4-point, you start to have non-trivial things that you can write, and then things are not completely fixed. Yeah? But the 3-point amplitudes are completely fixed. Okay. So any questions? Huh?
How color enters?
We will enter the color. Just, yeah, we will enter the color here. Yeah, so far this was just about kinematics. So you can also multiply it, and in Young-Mills theory, you will multiply it by some FABC, yeah, by some part, the non-kinematical factor, yeah.
I think I have a question on Zoom.
You have a question on Zoom?
Yes.
To have the interpretation of virtual particles for complex momenta. Okay, well, these are kind of 2 different things, yeah, because the virtual particles are not physical particles. So we will not observe them. They don't appear on external links. They are not on shell. So they are just kind of our constructs. Or it's an helper if you want to visualize in Feynman diagrams how things interact and so on. But they are not physical particles. These particles are completely physical. They just don't live in our world when we have real momenta. They live in some other world when everything is complex. Yeah. But in that world, we can build a collider and scatter free massless particles with no problem, and we will find these amplitudes. Yeah. So it's just the nature of our space-time. But other than that, they are completely fine, complex momenta. While the virtual ones are not actually physical, they are not physical states. Yeah, they just propagate on internal lines. They are not on shell. Anyway, they are not real particles. Yeah, while these ones are all real. Or real, they are complex, but they exist. Yeah. Yes, another question. For the 6-point amplitude, is the dimension -2? So this idea, it works. Yeah, this is only for 3-point. This idea is for 3-point, because going to higher dimensions, the amplitude is not completely fixed just by the little groups. Yeah, so you cannot run this argument. For example, this is not true. Yeah, the arbitrary 3-point amplitude doesn't look like that. Yeah, it can look arbitrary. Yeah, it has poles. This has no poles. Yeah, it has poles, and this only works for 3-point, this argument. Yeah. Beyond 3-point, you can still check that the helicity is correct, as we did with this Park-Taylor formula, but it doesn't fix it. Yeah.
Any further questions?
Okay.
So I think we can stop here. And thank you, Jaroslav, again.
Okay, thank you.